Hello, I'm Umnik, and today, after very long pause, I will write second division to the first round and try to explain what I'm doing. Okay, so in problem A, we are given two fractions, a divided by b and c divided by d. We want to make them equal, and what we can do is we can take one of the numbers and multiply it by some integer. We cannot multiply denominators by 0. Well, it should be clear that it's always possible to make it in two operations. Like, for example, we can multiply a by b times c and multiply c by d times a, like the initial a, and then both fractions will be just equal a multiplied by c. So like it's easy to check if they are already equal, so we don't have to do anything, in which case the answer is 0, and all that we need to check if one operation is enough. And for that, well, I guess we should look at the numbers a times d and b times c. That's how we compare the fractions. Like for fractions to be equal, a times d should be equal to b times c, and we can multiply one of those numbers by some integer. So we should check if one of them is 0, then we can multiply the other one by 0 and they will be equal. And if none of them are zeros, then to do it in one operation we should multiply the smaller of them, and it is possible only if the bigger of them is divisible by the smaller of them. So we just read for numbers a, b, c, d. Now we actually interested in a times d and b times c. If they're already equal, then we just print 0. Otherwise, let's make x the smaller one. If x is greater than y, then swap them. And if x is 0 or y divided by x, y modulo x is 0, so y is divisible by x, it means that we should print 1, otherwise print 2. Let's move on to problem B. In problem B, we're given an array of integers. We need to choose a proper subsegment, which means that we cannot choose a segment which equals the whole array. So we need to choose a segment which is not the whole array, and then we calculate max outside the segment minus minimum outside the segment plus maximum inside the segment minus minimum inside the segment. We want to maximize that value. Okay. We know that maximum in the whole array will be either outside or inside, and it will be the maximum of that part, and the same goes for minimum. So we are probably interested in let's draw something. We have an array, we have max somewhere, we have min somewhere. We can assume that they're different. If they're equal, then all the elements of the array are equal, and the answer is 0. And we have some cases, I guess. If we choose some big segment which contains both max and min, then like if we say that it contains max and min, we already know that inside the segment, like this will be max, this will be min. So we want to maximize max minus min outside the segment. Like if we include more elements in the outside part, it means that maximum will be bigger and minimum will be smaller. Like if we add new elements, it will increase maximum and decrease minimum. That's what we want. So if we choose this case, we actually want to choose like this segment, the smallest segment that contains max and min. Okay, that's like one of the possibilities. If we choose a segment that contains max but not min, that's a bit hard, right? Like we want we know maximum inside and minimum outside. So we want to minimize minimum inside and maximum outside at the same time. Like we want to minimize their difference, maximize their difference. And it is not very clear, actually. Yeah, I do not right now see a way how to make this work. But there is another way we can try. Let's talk about it. Let's look at the formula. We want to the formula is max outside minus min outside plus max inside minus min inside. Yeah, I'm sorry, I have a new graphic tablet and it's not working great. Yeah. Okay. So I want to maximize that. Because we want to maximize that, like it's not very restricting for us that we have to choose max element here and min element here. Like we want this thing to be as big as possible, this thing to be as small as possible, and like for all the parts it's what we want. So what we can do instead is to say that we will take any element outside minus any element outside plus any element inside minus any element inside, and we want to maximize that. We first choose the segment and then we choose two elements outside. One we will take with plus sign, the other we will take with minus sign, and two elements inside. One we will take with plus sign, the other with minus sign. We can choose the same element two times. Like instead of solving this problem that we are asked, we will solve this problem. What is going on? Why are you doing this? So how to solve this? We will do dynamic programming. We have our array. So if we choose some segment, like there are three parts of the array. We are splitting our array into three parts: before the segment, inside the segment, and after the segment. So we will do DP. We will consider some border and move it from left to right, and we will say that we have made all the decisions before this border but didn't make any decisions after this border. What are the decisions? Decisions can be to take some element on like these four positions, and the decisions can be to end the previous phase and start the new phase. So our DP will be the position of this border phase in which we are now, like 0, 1, 2, before, inside, and after. And mask of these four positions, like which of these four positions we have filled out with elements before this border. So when we move the border, we first decide if we want to move to the next phase, and then when we move the border one element next, we are eating one element. For this element, we have to decide if we want to put it on any of the positions, which positions can be filled out defined by phase. Like these two can be only filled out on phase 1, and these two can only be filled out on phases 0 or 2. And this thing will be to maximum value, like we only consider value of the function summing up the positions in masks that we have already filled out. This is very hardcore for B of second division, but some greedy with case analysis didn't work out for me, and this surely works, so let's try to implement it. The DP is on max, so we will initialize everything with minus infinity. Except in the beginning, we're staying before the zeros element. We are in zeros phase and we haven't chosen anything, and the value is 0 obviously, because our mask is empty. Function is just 0. We're staying in the same position. Before we move further, we can change to the next phase. We kind of have to check that we have at least one element inside the segment and at least one element outside. It is not very pretty, but we can ignore that. If we don't have elements inside or outside, we wouldn't be able to choose any element in the appropriate part, so we cannot fill all the 4 positions, so we just can't do anything illegal to obtain actual result. So we do not care about that. So for all the states in which it is possible to move to the next phase, so phase is 0 or 1, we say that it's a legal transition to move to the next stage. So from position, phase and mask, we move to the same position, phase is increased by 1 and the same mask, and the values do not change because we haven't added anything to the mask actually. I need to iterate over positions up to n inclusive to make this transition, because we can have a segment that ends in the end of the array, so I will need to move to next phase here, but now I will make transitions that eat up the next element, and if there are no next element, I don't know how to do that. So actually independent of where in which phase we are, for each element we can take it as maximum, take it as minimum, but it will depend on the mask, on the phase, to which positions in the mask it corresponds. So we have actually 4 transitions, at most 4. Okay, let's write them independently, choosing for max and min. So let's say take max and take min. Value, initially it's dpt pt mask, and we will have a mask, initially it's mask. If we take the current element to be max, we should increase the value by this element. The position in mask will be either 0 or 2 depending on the phase. So it's 0, but if the phase is 1, so inside the segment, it's actually 2. If this position is already filled in mask, then it's bad, and this transition is legal. Otherwise, we will fill up this position in new mask and proceed. The same for minimum. Let's just copy. We will decrease value by this element. The position is 1 or 3, and everything else is the same. If not okay, then just continue. Don't do the transition. Otherwise, we will make transition to state next position, still the same phase, but new mask. And here we're just printing the position after the whole array, phase 2 and full mask. I guess there should be much easier solution, but that works. In problem C, we're given a rectangular matrix with zeros and ones. In one operation, we can take something called L-shape figure, which is 2 by 2 square without one of the corners. It should contain at least one before the operation, and in the operation we change all the cells to zeros. Great. We want to do maximum number of operations, and we only need to print the number of operations. Okay, so it looks to me like maybe after the first operation we should be able to always choose L-shaped figure with only one and just change it to 0. Obviously, like, the number of ones strictly decreases after each operation. In the end, we will have 0 of them. So we can't make more operations than we have ones in the beginning. So we want to like make as small as possible number of operations that remove more than one from the matrix. We actually care not about the number of such operations, but the number of removing ones that does not give us another operation. And I would like to say that after one operation it's always possible to find L-shape with at most one. So let's say that we did some operation, so we have this L-shape of zeros. If we have one here, then we can take L-shape like this. So like I want to prove I want to assume that it is impossible to find such an L-shape after one operation and prove that it's possible. There should be such an L-shape, or everything is just zeros. So I'm assuming that it's impossible to find L-shape with exactly one, and I want to prove that all the matrix will actually be consistent of zeros. So we actually ended already. So if there would be one, there would be such an L-shape, so it should be 0. And then we can like go to right, and like if we have one here, then there will be L-shape like this. For example, undo doesn't work. For some reason, it does something very different. This is not good. Yeah, but like it should be 0 here, then should be 0 here, here and here, and we can like reach the border of the matrix. Do the same on the other side. So reach border here, and then in each column the same. It should be 0 here and here and here and so on. So everything should be zeros. After we apply one operation, the maximum number of iterations we will be able to do next is just the number of ones in the matrix. So we want to find initial L shape with smallest sum, and the answer will be total number of ones minus that sum plus 1 for the first operation. And we have to not forget about the case where everything is zeros already and we can't do anything. So let's calculate the number of ones everywhere and minimum number of ones in not empty L shape. For that, let's first calculate sum. If it's 0, just print 0 right away. Otherwise, let's iterate over the squares 2 by 2. For such a square, we will calculate the number of ones inside. If it is 0, it all consists of zeros and there are no L shapes with at least one, so we just skip it. Otherwise, if there are at least 2 ones, then we can leave out one of the corners in which we have 1 and have current -1 once in L shape. Otherwise, we just have to take the one we have. So if it is bigger than 1, then minus, and that's the minimum number of ones in L shape inside that 2 by 2 square. So let's update that. And now I'm saying that the answer is sum minus minimum plus 1. Problem D has some convoluted statement. So we are given an array of integers, and I guess in easy version the integers are up to 200, but in the hard version they can be big. We want to find maximum number m such that we can choose a subsequence of array A. Exactly, we are choosing array B of indices. It should be strictly increasing, like this, the positions that we choose in the subsequence. And the following property should hold for any p from 0 to m minus 2. Like basically we're looking at pairs of neighboring elements. The following inequality holds. Like the element on position bp XOR b of p plus 1 is strictly smaller than the element on the position b of p plus 1 XOR bp. So we XOR with the position, but not with our position, but with the position of the previous element. Okay, let's say that we have chosen some subsequence and we have neighboring positions x and y. We should have a of x XOR y is strictly smaller than a of y XOR x. It's tempting to like XOR everything by x XOR y. After that, here we will have a y XOR y, because x XOR x will be 0, and here we will have a of x XOR x. But this operation can have bad influence on the less than sign. But like we can think about it. How do we compare numbers? If we write both of them in binary, we find the largest bit in which they are different, and the one that has 1 there is bigger. When we XOR both numbers by x XOR y, if they had equal values in some bit, they will continue to have equal values in that bit. And if they had not equal values in some bit, they will continue to have not equal values in that bit, which means that the position of the highest not equal bit will stay the same. Okay, that's kind of good. Like we can, if we XOR by 1 here, it will change both values. So like actually when we compare these numbers, like if like in this bit where they're not equal, the right one should have 0. That would mean that before XORing it had 1 and so was bigger. Why did I want to XOR by this in the first place? Well, because after the transformation, this number only depends on x and this number only depends on y. So how can we choose this? Well, it's tempting to do some kind of dynamic programming. And I would try to do something like this. Like we're choosing our sequence B0, B1, B2, B3, and so forth. Even in the original form, like this, if we arrive at some element, it doesn't matter what was happening before. Like, so if we know that we have built this sequence and arrived at this element and everything was okay before that, like for this pair, this pair, and this pair, it doesn't matter what we had here, we only care about the number of elements and we want to maximize it. We want our subsequence to be the longest. But it's kind of hard to make transitions faster than in like for fixed element, faster than just check all the elements after us, because like this inequality is not very convenient. So yeah, what I want to do now is basically say that after I have arrived here, I will just fix the position of this highest not equal bit. So what does it mean? Like I know that I have arrived here, and let's say that that's our x, and I want to make transition to next element, which will be y, and I want to check that this inequality holds. So what do I need for this transition to be valid from x to y? I know this number. I do not know this number yet. I could try all the values of y, but that's too slow. Instead, I will fix the position, this position k, it's up to log c, and so I fix k. So what do I know now? Like I look at this number. Come on. In binary, and there is a case bit. So what do I need to know? I need to make sure that this number actually has 0 in case bit, and this number should have 1. So for this fixed case bit, I know that we have something in higher bits. It should be, if we are looking at a, y, XOR y, like this part should be the same. This bit should be different, so we have not equal here. Right. And also, like I know this now, so I can look at its case bit and determine what should be the case bit of y. And let's say just start. So what now? Basically, I want to split the transition in two. Like for this x, I will try all the values of k. There are log c of them. Store something, and I will have like all the possible like left part of transitions, and when I arrive at y, I will look at this number. Now I know it. Again, try all the possible values of k. And make the transition that is the best for me. For fixed k, I know that everything before k should be, like higher bits should be the same. This bit, case 1, should be different, and after that, anything. So I have like fixed prefix of number in binary. This suggests that we should use trip for that. Not trip, try. Binary try. We will store numbers in binary try. So basically each node in the try correspond to some fixed, like this node says that prefix of the number is 0, 1, 0, and we know the k obviously for this node. And so like for each node we will store the best dp value of this x like for this prefix of length k, which correspond to a node in the binary try. We'll store the best TP value, guess we should remember about this. So we will actually store two values, one for AX that has 0 in case bit and one for AX that has 1. And so when I arrive at Y, I start to traverse the same try with my number AY XOR Y. And for each K, I will try to go in the other direction, the other sum. So if my number is something like this, I will try to go here and here, and then instead of going here, I will go to the other sum and choose the best DP value that is stored in this node, in the try, which has like correct value of case bit, the same as my number Y has. And from all of that, I will just choose the best possible option and make the transition. So all of that should work in unlocked set time. So to recap, I'm doing just DP of position. In each position, it means like the longest subsequence ending in this position, so that everything before is good. I try all the positions from left to right, and when I arrive at the new position, for all the previous positions that can be like to the left of me, they are all stored in try, like not actually the DPs, but like for each position and each K, it corresponds to a node in the try, and in each node I store the best DP for 0 or 1, in this case bit of A of X. So that's all stored. And when I want to calculate the DP for position Y, I again traverse the tree with try with this number. In each node, I try to go to the other sum and look at the DP value there and update my current DP with that. And yeah, I'm saying that after I have done that, I will have correct value of DP, and then I have to add this DP back in the try. Let's try to implement it. So for the try, we will need, well, kind of n times log C, which is 30 nodes. Actually, it's smaller than that, not by, like, not a lot smaller, but we can, like, we know that on the level K, there are at most 2 to the power of K nodes. So on each level, we will have at most 2 to the K nodes and at most N nodes. Because for each position we add only one number in the try, and like summing up the minimums will, like, for the upper levels we just can't have N nodes, so like I can actually cut that in half, probably, but I think it should be okay. Like, I'm not very low on memory, so it should be fine. Like, for each node I should store 2 suns and 2 GP values. So that's 4 integers. So that's 40 million integers, which is 160 megabytes. It should be okay. Let's clear the try from the previous iteration. I will use 0 to indicate that there is no sun. It is kind of dangerous because I'm also using 0 as the root, but like no vertex can have root as a sun. So if there is 0 in the like where sun should be, I know that it doesn't mean root, it means that I have no sun. So this is my number for this position, ax XOR x, or ay XOR I, basically number XOR its position. So first thing I'm doing is I want to calculate my GP value. So I'm considering that I'm staying at y, traversing the try, each time trying to go to the other sun and take the correct value of GP, update my GP with it. Starting in the root. Oh yeah, in the beginning the try says 1 because we always have root. So I'm iterating over bits in the descending order. So C is value of case bit in my number X. But before going there, I should try to go to the other sun. If the sun exists, I want to update my GP with try GP of vertex U and case bit of a j with which we are updating it should be the same as case bit in my position, which is I. So I'm saying take k's bit of I. Now I should go to the like myson, but if it doesn't exist, I should break. Like I'm going to the nodes that weren't visited before, so I will not update my DP from them. Otherwise, I go to this sum. DP I++. We should be careful, but it should be correct. Like we're starting from 0. If we didn't update with anything, we do ++, so it means that we can always have a subsequence that end in this element of length 1. Yeah, that's true. Just take this element as the first one. We didn't have to check any conditions, so it's always fine. And if we did update, then we updated with the length of previous subsequence, and now we increased it by 1 by adding our element, so yeah, it's ++. And now once again we should traverse the tree. Let's just copy this cycle. We are not doing this now, but in each node now if there is no such vertex, we should create it. And in this vertex we should update try dp of AI. Look, when we will be looking at it, this node corresponds to k's bit, and like the second parameter should be k's bit of our number AI. So we're updating this position with our delivery and printing the answer. In problem E, we again have a matrix. Now it's a square matrix, n by n is up to 500. And we also have a goal number k, which is from 1 to n square. We want to make the smallest number of operations such that after all the operations there are exactly k distinct integers in the matrix. In one operation we can choose any square submatrix and assign some number to all the cells in that submatrix. This sounds very very hard. Like, let's look at the problem on one dimension first. If we have an array and we can choose subarray and assign some number, then the answer is always at most 1. We can if we need to decrease the number of distinct integers, then the answer is at most 1, because like we can always do the operation prefix and like always assign 1 on some prefix. If we choose like prefix of 0 size, then we will have more distinct integers than we want to, and if we choose all the like prefix that coincides with the whole array, then we will have 1. If we slowly increase the size of the prefix from 0 to n, the number of distinct integers will slowly decrease, and by slowly I mean by at most 1 each time, so we cannot skip our target value. That's called like continuity, but like in a discrete setting. If we need to increase the number of distinct integers, we cannot do much. Like in each operation, we can only introduce one new value, and it's always possible to increase by 1. Like let's take just a cell which is not unique. We have at least one of those if we don't have like all the numbers unique. If we want to increase, then we don't have all the numbers unique. So we can take choose a cell which has a non-unique number and replace it by the number not present, so that increases the number of distinct numbers by 1. And actually, I didn't use that the problem is one-dimensional there, so for 2 dimensions it's the same. So in the beginning of the solution, we should just count the number of distinct integers we have, and if we have exactly k, the answer is 0. If we have less than k, the answer is k minus current number of distinct integers, because in each operation we can increase only by 1, and we can always increase by 1 if we want to. So that's optimal. So the problem is decreasing, and as I said, on 1 dimension we can always do that in one go. And I want to say that in 2 dimensions we can also always like use constant number of operations. What's the issue? Like why can't we just do like apply the same logic? Well, because we don't have continuity now. We can start by like applying operation on square that has the same upper left corner with the whole matrix, and when we increase its side, we add a lot of new elements. But like so what's the issue? The issue is that we can skip the target, right? Like increasing, and let's say that after going from this one to the next, we skip the target number. We had more than k for this border, but less than k for this border. If we instead somehow add the numbers in like the cells in this area one by one, then it will be fine. But we can't do that. But what we can do is we can just apply the operation on the smaller square first. We still have more than we want. But now like we can try to add these elements one by one. Let's say that first we add elements here from up to down, not including the corner element. And then we add these elements from left to right. And let's say that we need to stop when we arrive here. So what can we do? We can apply the operation here first, then on the same square but shifted one to the right, and then we need to cover these elements so we can do this. We know that we will stop before reaching the last element because we knew that like bigger square is already bad. So we can always reach the target in 3 operations, but 3 is bad. Like if we could always reach what we want in 2 operations, then like we have hope. We have hope of saying that okay, we can always do in at most 2. We know that we need at least 1 operation, so we only need to check if 1 is enough. And that probably can be done by just trying all the operations somehow. I'm not sure how yet, but like what I'm saying is that try to apply 1 operation is much easier than try to apply 2 operations. So what we want to do instead is to somehow like we want to prove that it's always possible in 2 operations. How to do that? Well, let's start from the same thing. We're trying to apply the operations with upper left corner in the upper left corner of the matrix. If we find the target we want, we just done in 1 operation. So let's say that there is this jump. What I want to do is like I kind of want to apply the operation like here and here, but the issues are like we will not cover this thing. No, that's not good. Like ideally, I want to add elements one by one, such that like now we have continuity. So if we would be able to apply the operation on exactly that area we are done, but like we only can apply the operations on squares. So I want my area to be coverable by at most 2 squares. Maybe with some tricks. There is an issue that like I don't actually have to prove this. If I can just believe that it's always possible, like I actually have to only believe that in case when we need to decrease the number of unique elements, the answer is always at most 2. If I believe that, I can just focus on like how to check that answer can be 1. But like I like to prove stuff. Like I have proven that the answer is most 3. Can we do better than that? Right. We need to look at it a bit differently. Like when I'm saying that for this square, if I apply the operation with 1, it has like the whole matrix will have less than k unique elements. what does it mean? Well, I'm kind of erasing all the elements inside, but after that adding element 1 if it wasn't present. Well, if it was present, I'm also adding, but it doesn't increase the number of unique elements. So we can look at like this is a square. Well, first, if I actually stop like while adding these elements, I will totally be okay with two squares, like this one and this one. Well, basically, like I had green ones, but without the right one, because I didn't have to cover this additional column, just this. So if I try to add this and I'm done, that's good. If I'm trying to add this independently and it's good, I'm done. Otherwise, well, basically, we need to change the order a bit. Like, I know that adding ones here is not enough. Let's then add this element, the corner one, and then we will add this one, this in this order, changing the sides each time, and like one square will be this, and for the other square I kind of increasing from this side, but each time I'm adding two elements. The issue is that, well, again, it's not exactly continuous. We can, because we add two new elements each time, we can jump by 2, and again we can skip the target value, but we can skip it only like by 1. And we don't have to apply the operations with the same value for this square and this square. So if we jump by 1, it means that if we apply 1 here and 1 here, the number of unique elements will be 1 less than we want to. Well, okay, instead of applying 1 on this square, let's apply something else that we don't have after applying 1 on this square. It will be the same as applying 1, but 1 new unique element, so we'll have exactly what we want. So that proves that if we want to decrease the number of unique elements, we always need at most 2 operations, and now we have to somehow check that we only need 1. Well, I guess we will just try all the squares. There are n cube of them, but we have to somehow basically calculate the number of unique elements if we erase this square, and if we get k or k minus 1, then we are done, because we can do +1 by coloring this whole square in something that we didn't have. So we kind of need to check if we can remove all the occurrences of some, like we have to calculate for how many colors we have removed all the occurrences. only 246 megabytes. Oof. Like I think that I know how to do that with N-cube memory. Okay, let's first iterate over the size of our square. And for fixed size, so fix the length of the side. Then we can go through all the numbers. So this of n options. Go through all numbers. There are of n square of them. And for each number, like we can basically we always cover a square. Square is a rectangle, so we need to cover the bounding box of all the points of that color to completely remove that color. So we can like first determine the bounding box. So let's say that like, this is our matrix, and for some fixed color, this is the bounding box of points of those colors. So we have point on this side, point on the upper side, maybe two, maybe it's in the corner, but like we have to cover this rectangle to cover all the points of this color. We know the length because we have fixed it. So now the square is described by its upper left corner, and we want to understand for which upper left corners we will cover all that. Well, that's kind of easy. It's independent on the coordinates, so the left corner should be like to the left of this side, but to the right of this side minus len, because it should cover it. And something similar for the upper corner. So if our upper left corner is inside this strip and inside this strip at the same time, so it should be in this rectangle, then it covers all the red points. So I want to do +1 on this rectangle and then sum it up over all rectangles. I am doing that in offline, so do +1 on rectangle, then like to do +1 I will do +1 here, -1 here, +1 here, -1 here, and then to check the sum in the cell I have to calculate 2D prefix sum. Like what's here? It's well-known technique. So for fixed len, I'm doing everything in of n squared. Like I'm going through all the numbers in of which there are of n squared, for each of them. In of 1, I'm doing +1 on the rectangle of line by changing 4 positions. Then I'm calculating 2D prefix sums. And then for each upper left corner, I know how many colors have I removed. So I will be able to check if after removal I have exactly k or k-1 unique colors, and that should do it. The whole solution in cubic time, and we have like half an hour to implement it. Should be more than enough. That's a nice problem. So for each number I want to calculate a bounding box, we will initialize the bounding box by saying that left and upper borders are +1, right and down -1. They're from 1 to n square, right? Cool. Okay. Now I need to calculate how many different colors I have in the beginning. And actually I only interested in its difference with k, so let's just do k minus minus. If k is at least 0, then the answer is k. Because it means that we want to have more unique colors than we have in the beginning, and more like exactly by k, so we need k operations, and it's enough to do k operations. And otherwise we have the harder part of the solution, and we're saying that we need to remove k colors or k plus 1, because after removing k plus 1 we can add one new k, I mean after multiplying by -1. Like we have more by k than we want to, so we want to remove k or k plus 1. Iterating over 1 and basically like solve 1. And if that didn't succeed, then print 2. So if we find a square which is good inside solve, we will just print 1 and terminate the program. It can be optimized here. Like for example, I can say that I only need to clear this like up to n-len here, because like if I know that the length of the site is len, then the upper left corner is strictly smaller than n-len by both coordinate. Not strictly smaller, at most that by both coordinates. So we have this color. So our left upper left corner should be like first coordinate should be at least b of I1 minus len plus 1, right? I want to be able to cover this x coordinate. So if x coordinate of upper left corner is strictly smaller than this value, then it will end before covering this. And it should be at least 0, obviously. Like if we have some bounding box like very upper left part, but len is big, this number can be negative, but obviously our coordinates will be from 0. And x2 is if I0 plus 1, like this is fine still, this is not fine already, and the same for y. If this rectangle is not a rectangle actually, like if x1 is greater than x2 or y1 is greater than y2, then this area is empty and we shouldn't do anything. Otherwise, we want to add +1 on this rectangle in offline, and that is done by doing this. this way, like we calculated the sums. So if the sum is equal to k or equal to k plus 1, that's it, I think. I'm not sure that samples check anything, but I'll just submit. Not even that bad, actually. Considering that I spent like 20 minutes on B. Alright, thanks for watching. I hope it was educational in some way. Bye.